Okay, hello, 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 hello.
I don't look at the schedule because it's more fun.
This clock is working again, right? Yeah. Oh, yes, excellent. So can you hear me in the back? Because it seems mildly on, yes? Okay, great.
Yeah, we turned off the mic a couple of times. Do you want to introduce Sakura? Yeah, sure.
I can also. So I will write down my title so we know what we're going on about.
So for our second lecture of the morning, we are very pleased to have Sakura Schafer-Nameki from Oxford. She will be speaking about generalized symmetries and geometric engineering. So welcome, Sakura.
Okay, thank you very much. So thanks everyone for being here in this lecture and for the organizers for putting together this fantastic school. I think this is sort of maybe the year or the last 2 years for sure, where symmetries and generalized symmetries really have taken off and have become sort of this explosion of new results. So it's a very timely sort of place and space-time sort of location to be in to actually work on this and learn about these things. And over the next 4 weeks, you will hear a lot about what these generalized symmetries are. And my lectures will sort of be combining both symmetries and geometric engineering, which is sort of more string theoretic, high energy perspective. So those of you who are condensed matter physicists will probably say, okay, I don't know anything about this, but you should all learn about this. And essentially my first lecture will be all about what actually are these generalized symmetries. I will talk about continuum field theories. So unlike Nadi, who was working on the lattice, was focusing most on the lattice, I actually will be focusing on continuum field theories. However, all these recent developments that essentially came out of high energy physics in D, so D being space-time, so for those of you who are condensed matter physicists, D plus 1, D minus 1 plus 1, the first identity of the day. It's essentially sort of, it's coming out of D basically being 3 or 4, also higher dimensional quantum field theories, but many of these things will also work on the lattice. So a lot of these generalized symmetries, higher form symmetries, higher group symmetries, even non-invertible symmetries, that you'll hear about, they will all also have a life on the lattice. So if you're a lattice person, you shouldn't shut out the story. You should actually learn it and then learn how to actually put it on the lattice. And that's sort of an enterprise that a lot of condensed matter theorists are actually pursuing. Okay, so that's sort of the preamble to where this whole set of lectures will be located. I think Nadi made a very strong point that, you know, symmetries are an extremely important tool in physics, in quantum field theory in particular. But really, why we're talking about these generalized symmetries is due to sort of a key update of what actually, and that came sort of 2014, what actually comprises a global symmetry. So global symmetry in the last lecture was what I would call a zero form symmetry. And we'll actually discuss exactly what that means. And in 2014, a paper by Gallardo I actually will not be giving any references except for this. Gayotto, Kapustin, Seiberg, and Willett. What actually we should think of as a symmetry of a quantum field theory in any dimension really is so abstracting it out, and their slogan was identify a symmetry, so a global symmetry of a QFT is basically something which we should think of as a topological operator. So it's this identification which we'll discuss today, and I'll give sort of motivation why that makes sense, even from the point of view of just a standard symmetry as you know it, from global symmetry, but then also why it makes sense to then extend this and pass to something that you could then call generalized global symmetries. So examples of such things are, of course, you know, the examples and I will make this precise why exactly there's a topological, this may not be clear to you why there's a topological operator associated to a global symmetry. Examples are, of course, zero form, and you don't know what that is, so what you normally would have called a global symmetry. So like what you had in the last lecture. So these are symmetry groups G. And so a group has composition, it has an inverse, there's an identity object, an identity element in the group, and every group element has an inverse, and it acts on local operators, right? So that's sort of the key feature. So these actually act on local operators. And the extension, which came sort of from identifying this with just topological operators, was, well, we could consider extended operators and ask what kind of symmetries could they have, and this sort of led them to these so-called higher form symmetries. And there are still now groups, and I'll call them sort of P, a P-form symmetry. This just sort of, at the beginning, just take it as a label. They will act on P-dimensional extended operators. And again, for the condensed matter people, P is the space-time dimension of the operator. So when I talk about a line operator, I really mean a line operator, not secretly a surface. Okay, so this is essentially you're going away from a local operator, which is zero-dimensional, to now P-dimensional operator. And so this is essentially, this was the 2014 extension. Now, what then emerged is there are many other extensions of what actually a global symmetry can be, even if you combine these two things. And so there's this third thing is it's called a higher group symmetry. And this essentially is if you have a P-form symmetry and a standard global symmetry, they may not form a product, but something more complicated. So this is like an extension of a G0 and GP, but still everything is in the realm of groups. And so what Nadi was telling us in the last lectures, when you have a group symmetry, you can usually study representations, right? So everything will transform in some kind of representation of the symmetry group. So for example, for a zero form symmetry, we saw local operators will transform in some kind of representation. Likewise, if you have a line operator, it will actually transform in some representation of this group. And the same is true in this more complicated case that we'll consider. But then actually the reason why I think also there's been a lot of, in the last 2 years, activity is that all of this is sort of natural and once you identify global symmetries with topological operators. But once you actually do that identification, nothing stops you from looking at things that aren't groups. So in fact, the latest update is here, scrap the groups. So no more groups. But I actually extend this to something which is sort of non-group-like. And the best way you should think about these types of symmetries is in a first approximation as algebras. So in fact, once you have a symmetry that isn't sort of, every element has an inverse, there's an identity object, and there's a sort of this composition that's group-like. So G times H is GH, and that's again in the group. An algebra has a much more complicated structure. It will actually have composition of two things will be the sum of other things, right? So of other generators. And so these are the so-called, well, the dubbed non-invertible symmetries. And that's sort of the latest generalization. Now, Yifan's lectures, I believe, in 2 dimensions will discuss these things, and they have a very long, rich history in 2-dimensional conformal field theories, also in condensed matter physics. But here we're really talking about d-dimensional quantum field theories, where d, the space-time dimension, is 3, 4, 5, 6, where we have such non-invertible symmetries that are not group-like. And so I think over these next 4 weeks, you'll see exactly how such symmetries can still be sort of sensible in the context of quantum field theory, how they're realized, and then potentially also what actually replaces the representation theory of groups once you have a symmetry algebra. Right? That's not so clear. So Nadi's point was when you have a group symmetry, you have a faithful linear representation of it on the operators. Now here, when this is an algebra, what replaces that kind of question? Right? What actually is the analog of that? So that's sort of eventually where we'll be heading. So this is sort of the generalized symmetry part of these lectures. And I think both high energy, condensed matter people should connect to this. The other part is string theory. So now here's, since Nadi asked these questions, who actually has taken a course in string theory? Okay, fantastic. Now, who has taken a course in superstring theory? Okay, amazing. Okay, so you all know what also M theory is. Okay, fantastic. Because this was one of the questions that was worrying me at some point, but obviously completely in vain, unnecessarily. Excellent. So the second point is, so what is this connection to geometric engineering? Now, so string theory is a way of constructing quantum field theories, but more importantly, of course, quantum gravity theories. Geometric engineering, essentially, is a particular limit of string theory, where we just focus on quantum field theory degrees of freedom. We decouple gravity. So this is essentially, this is a limit of string theory, or M theory, where we decouple gravity. And we only focus on, say, quantum field theory degrees of freedom that string theory models for us. Now, why exactly is it interesting to study such a thing in the context of these types of generalized symmetries, or just full stop? Why is this an interesting question to study? So this gives sort of a way to construct quantum field theories, QFTs, usually with some amount of supersymmetry. And you might say, okay, maybe this is a nice way to construct quantum field theories and to actually get some more interesting information about them. But really, the key is some quantum field theories we know so little about that this is the only way to really get some interesting sort of description of them. So some QFTs will essentially rely on such a construction. So just even arguing that they exist is heavily based on such a construction in string theory. And examples of these are so-called conformal fixed points. And now not in your favorite 4 dimensions or maybe 3 dimensions, but in 5D and in 6D. So in 5-dimensional, 6-dimensional space-time dimensions. So I will explain in a moment why this is an interesting proposition. Does anyone already know why this is sort of a peculiar thing to even discuss? Say, if you look at a gauge theory in 5D or 6D, what is wrong with that? Like, you know, Nadi was drawing this diagram of there's the UV and there's the IR. And usually we go from the UV to the IR, so we input a UV, some, you know, yes, please, Sebastian, I think, I remember. That's right. Okay, so in 5D and 6D, mind you, 1 over G squared trace F squared term, right? This here, this looks like it's an IR-free theory. Because the mass dimension of this, so if our space-time dimension is d dimensions, right? So for 4 dimensions, this mass dimension is 0, but for d dimensions, this is actually 4 minus d is negative. So when you look at this problem of writing down a gauge theory in 5 or 6D, then this may not be, okay. This may not be something where you would think you would find particularly interesting fixed points in the IR, but actually one of Nadi's results in the 90s, so I think, was in fact there do exist conformal fixed points. But these are UV fixed points. And in fact, they happen at G equals infinity. So anything that you try to do, describing them with some perturbative Lagrangian methods, will somehow fall short of capturing such an intrinsically strongly coupled theory. And one thing that we'll see is that in fact it's crucial, so it's key to construct these such theories in string theory. Right, and then exactly this story of how this is done then resulted in this famous work of Intriligator, Morrison, and Seiberg, where only Morrison is not in the room. Okay, so this is one of the motivations for why it's interesting to study quantum field theories in string theory, because it gives you access even to this g goes to infinity limit. And how is it done? Well, it's done by what you call geometric engineering. So the tool is we feed in, we have quantum field theory questions. We would like to construct, say, so some QFT questions, such as we want a 5-dimensional supersymmetric CFT, so conformal field theory, fixed points as the CFT. We want to study the limit g goes to infinity, or g equals infinity. There's actually a ladybug right here. It's kind of peculiar. Anyway, so it's enjoying this lecture too. Anyway, so g goes to infinity. And so how do you actually do this? Well, you translate this into a geometric problem, where this here becomes a limit in the geometry. Right, so you have essentially a QFT input, you translate it into geometry, and then you access this infinite coupling limit. And so this is sort of the story. And this particular dictionary here is given in terms of M theory. And the types of geometries we'll discuss are so-called Calabi-Yau geometries. I'll explain to some extent what these are. Who knows what a Calabi-Yau geometry is? Okay, so we are really ready to roll. Okay. Ken was telling me, don't worry, they will know everything. So I worried, and I shouldn't have worried. Okay, so this will be amazing. But okay, like with Nadi, I would like you to ask questions, right? I mean, now I'm just giving you a very broad brush overview. Once we get into the details, I would like you to stop me. This is just to set out why we're doing this at all. Okay, so this is one of the sort of setups why this is interesting. It gives us access. And now, of course, when you have such a strongly coupled quantum field theory, it would be nice to also understand its symmetries, its global symmetries. And in fact, there's some interesting thing happen when you actually go to this infinite coupling limit in these theories. For example, even in terms of the zero form symmetry, so this standard global symmetry, there's a non-trivial enhancement. So the UV has a larger symmetry group than the IR. So that's sort of this group homomorphism that Nadi was talking about. But then also what we'd like to know is how do we characterize extended operators, right? These are in the IR, these are gauge theories. There'll be line operators. What happens to them in the UV? What kind of symmetries do we have? And also what kind of Toft anomalies do we have? And so these are the things that we'll actually calculate from this geometric setting, because in this case, this is sort of the way to describe these things. Okay, there are other motivations. This is one motivation. There are two other motivations. So why study this sort of thing in the context, symmetries in the context of string theory or M theory. So this was number one. So this is one. Two is, so more, once you actually look at quantum gravity, there's this whole swampland program, if you would like. And one of the statements here is that global symmetries are not consistent with quantum gravity. They either need to be broken or gauged. And so one of the questions is when you have a string compactification, say you start off with something in a geometric engineering limit where gravity is decoupled, so you do still have global symmetries. What actually happens as you now, bring the volume of this compactification space to finite size to these symmetries? So in fact, to understand these type of questions, you also need to know how are the symmetries actually encoded in the string theory background. So that's one motivation, and then the third motivation is, which maybe speaks to many of you also, is holography. So many string theory backgrounds with, say, an ADS or some flat space, Minkowski, have some holographic dual descriptions. And now you could ask, how are the symmetries of the dual QFT, right? In the ADS case, the CFT, and the Minkowski case, the QFTs encoded in the supergravity or in the string theory. And so what these lectures should tell you is how exactly you will, if you compactify string theory in whatever way you like, how you should actually compute symmetries in all these types of settings. But we'll start with sort of this construction here, and then we'll see how far we get. Okay. So the plan, this is again a tentative plan. We'll see how quickly we move and how many questions there are. The first chapter will be just an intro to generalized symmetries. And that will probably take most of today and some of tomorrow. And then the second chapter will be about sort of geometric engineering. And I'll focus on M theory, realizations of 5D supersymmetric conformal field theories, and I will actually discuss everything in the context of a pure SU2 gauge theory. Right? So if you said, I don't know what these 5D CFTs are, and this will be very complicated, I will really be discussing all of these aspects of these symmetries, zero form, higher group, in the context of the pure SU2 gauge theory, which, again, Nati discovered in the 90s. So a lot of these things really go back to Nati. So he really should be giving these lectures too. Except maybe the two-group part, okay? So there's a pure SU2. It couldn't be simpler. But already a pure SU2 gauge theories will have extremely interesting aspects in the strong coupling limit that we'll be discussing. And then the third part, and that's sort of a function of speed, is then going to be what's called sort of some slight dissymmetry TFT. There's a particular way of thinking about symmetries, which actually will be realized here. It will also capture symmetries in the geometric engineering, and it's kind of sort of the everything, everywhere, all at once of symmetries. And but it's much more simple and elegant than that reference. Okay, which is probably not difficult to do. Okay, so this is the plan. For Conant's matter theories, the symmetry TFT will be known to you as a categorical symmetry. So this will be very confusing if you're a Conant's matter theorist and you've heard that word, but this is what I mean by that. And I'll construct it from the point of view of a string compactification. And actually, anomalies will also be part of this symmetry TFT. So it'll essentially contain all these things in one theory. Okay, are there any questions so far about the scope, about, I'm not excited because you know everything about string theory, and so I can actually start with the lectures. But are there any questions, comments? So I think we're ready to start. Good. Okay, so generalized symmetries. We start with this observation. Symmetries are topological operators. And I would like to show this in the most basic setup, namely that of a standard global symmetry in quantum field theory. So this is really sort of a recap of global symmetries in QFT, but put in a slightly different language. So then we see these topological operators, and then it'll be very natural to then extend it to these higher form symmetries. Okay, so let's recap what actually is a symmetry in just a classical field theory. Well, this goes back, so in classical field theory, right, this goes back to Noether, 1918, so almost 100 years ago. So if I have some theory with an action S and a symmetry, so I vary it with respect to the symmetry, the action vanishes, then in fact this implies there exists a conserved current. So I will write the conserved current once as sort of d mu, j mu is 0, but actually I can also write this in terms of differential forms as d star j is 0, where this here is sort of a 1 form. And this is now a question. This is clear, this notation. To whom is this clear? What is d star j? Okay, so I need to explain that. So I will use differential forms relatively frequently, so we'll need to explain a little bit what they are. So when I write d mu, j mu is equal to 0, I actually can also sort of define in differential form, so differential form notation, I can define sort of the current j as just dx mu, j mu. So I just take this differential along space-time and contract it with j mu. Now, there is the operation, which is the Hodge star operation. Hodge. And this acts on differential forms. So let's say omega p is the set of sort of differential forms, x1, xi1, which dx ip. So I take the antisymmetric wedge product of these p differentials with some omega I1 ip. So that's just an antisymmetric p tensor. And I just contracted this with this dx thing. And this makes it a p form. Now, one operation that you actually know on this is just taking a derivative. So d on some omega like this will actually be in omega p plus 1. How do I see this? Because this d is just defined as d by dxi, dxi. So if that acts on omega, right, I will take the derivative. So this is equal to now dxi omega so here the x. So okay, so I will let me get my indices straight. So this omega was from I1 to IP. So then this d by dxi sum will be giving us something that is dxi omega I1 IP, and then actually contracted with dx I wedge dxi1 p. Okay, so it gains a differential because I hit it with this total derivative. So what the Hodge star does is essentially it maps it to a dual object. So the Hodge star maps an omega p form to omega d minus p. And usually I actually put a subscript d, which means I'm actually taking this in d dimensions. And this actually is a very importantly, it depends on a metric in your space-time. So the star of some omega is basically omega. So actually, let's do this for this particular example of this j. So star of this j will be just simply j mu epsilon mu mu1 to mu d minus 1 x1 mu1. Okay, so it essentially transforms here this one form, this j, into a d minus 1 form, which is here. So this is a d minus 1 form. So now if I apply d to star of j, it just gives us d mu j mu, and then a d wedge product of forms. So in fact, d star j is just going to be essentially d mu j mu, and then times sort of the volume form of our space. And so in the sense saying that this is 0 is the same as saying that d mu j mu is 0. Okay? So this is essentially what this form notation will mean, that I will use probably throughout these lectures. Okay, so conservation means in this language that d star j is equal to 0, and then we know also there exists sort of conserved charge. This is all still in the context of Noether's theorem, so everything is still classical. So there's a conserved charge. If I take md minus 1, this is a spatial slice, and I integrate exactly star j over this. Right, this is now a d minus 1 form. This was a 1 form, this is d minus 1 form, subscript d. Then this is conserved. Okay, so this is essentially nothing other than what you know from classical mechanics. So what I'm actually now going to do is ask, can we rewrite this now if we go to quantum field theory and we discuss now sort of symmetries acting on operators, we'd like to actually formulate this in terms of topological operators as per this general correspondence here. So we need actually, so I should not use this board. Okay, so I need to clear this. And are there any questions about these differential forms? Now might be a good time to ask this. Okay, so this was classical. Now in quantum field theory, you all had at least 2 courses of quantum field theory, so symmetries imply ward identities. And one way of phrasing them is if I actually have a transformation, phi goes to phi plus, say, epsilon delta phi, and I can apply this to correlation functions, then actually what I get is the following type of relation. So if O, P is an operator at the space-time point P, then I actually can write down the following word identity as a d-dimensional delta function, x minus P. If I vary this operator, this is the same as inserting this as d star j O of P. So this equation here becomes a little bit more transparent and intuitive if I integrate this over the full space-time. So that's actually MD. MD is here our space-time. If I integrate this delta function will just say, actually here it should be, it doesn't actually matter. Let's put it at x, actually let's put it at p. So here this delta function, it just says x is equal to p. And actually here we integrate up this here. And what we find is the following relation that on the, so this integral over md dx, this is equal to the right-hand side integrated md d star j. Now this is our space-time. We can actually use Gauss's theorem and then write this actually as an integral over now a d minus 1 dimensional slice. I'm thinking of this as, in sort of projection, this is MD, and this is the boundary of MD, which is an MD minus 1. Then this actually is just now star J O of P. And this star J now integrated will just give us Q. So this is actually Q of MD minus 1 O of P. Okay? So what we find is that this integral here, when this is non-zero, then this is just given in terms of inserting now this conserved charge on this operator O. Now, when exactly is this integral non-zero? Yep. That's not possible because this is the fixed one. Okay, so this part from here on, you just use Gauss's theorem. You all know what Gauss's theorem is. Applied to a space that's d-dimensional with a d minus 1 dimensional boundary. Okay, so I will write down the final thing here, and we'll try to use less board. Okay, so what we found is integral, this is our space-time, delta function d x minus p, O of p, is equal to, on the right-hand side after this calculation, as a bit of an overstatement, is q md minus 1 O of p. And here, there should be a delta. So let me draw this picture again. There's an M, D, there's a boundary, MD minus 1. So when exactly is this side here non-trivial? So we have some operator that's sitting at a point, at a space-time location P. This is where O of P is. This delta function will be non-zero whenever P is inside this volume MD. So iso color here. So inside this volume, okay, this color just looks like white. Let's try green. So here is this point P. And so if this P here is actually in MD, so if P is inside this volume MD, then this charge Q of O is non-zero. Right? And if this point P is outside, right, here we're integrating over all of space-time, so this will, if there's a charge operator, right, this will actually carry a charge. But you could think of this, we'll think of this more generally, some subspaces. So here the crucial thing is P is actually this volume MD. Another way of saying this is it's inside the volume that's surrounded by this MD minus 1. So mathematically, what you would call this, it's a little bit of a sort of fancy terminology, but we would call this that P actually and MD minus 1 link non-trivially. All that it means is P intersects non-trivially the volume that's filled inside MD minus 1, okay? That's one of the key. So I'm not supposed to use this here. I think if I didn't do this, I'll be definitely writing there. Okay, is that clear, right? So the crucial difference between P being in there or not is that it's actually inside this volume, and this is what we call linking. So at the moment, this feels a little bit, artificial. We all know how to calculate charges of operators. But what I'd like to do is actually now, so think of this equation here in terms of just saying that Q D minus 1 O of P is then essentially the linking of MD minus 1 and P times, and this is the linking. Yeah, and it's defined as P intersected with MD such that the boundary of MD is MD minus 1. So in the simplest case, you have literally a disk, and you're looking at a point on the disk versus then you're looking at the boundary, and you're saying, is that P inside this boundary manifold or not? So already here we're seeing one important point. It's not so important what exactly the shape of this MD minus 1 is, right? Because all we did is, right, we used Gauss's theorem, and I'm drawing these as sort of almost spherical things, but I'm actually being very agnostic as to what exactly these spaces MD and MD minus 1 are. All that we need is that in that case, P is contained. And so we could put dense into MD minus 1. We can actually change this around. As long as P is contained, it doesn't actually matter, right? The result is the same. So the dependence of L on the precise shape of MD minus 1, in fact also of P, but P is just a point, is very mild. In fact, we can deform MD minus 1 to some MD minus 1 prime, as long as P is still contained, is still inside the volume. And this is sort of this topological nature. It doesn't really matter what kind of geometry it has, as long as this one topological condition that its piece contained is satisfied. Yes, please.
So here n minus 1 needs to be a closed.
That's right, yes.
But like in UFT,
yes,
flat space,
good point. Yes.
usually the spatial slice is like
That's
the plane.
That's right, yes.
Always
So, right. So actually, I'm doing this on purpose that way because we will actually very quickly go to Euclidean space. This is probably the only time when I'm really in Lorentzian space signature. Here you should really think of this as I'm integrating over this MD minus 1 here, right? You have some normal direction, you're just integrating transverse to this. Here is the time direction, and you're integrating over this MD minus 1. So you have some compactly supported things, and so this is still well defined. But actually, later on, we'll completely relax this, and MD minus 1 will be some compact, sub-manifold in our full space-time when we're doing these more general constructions. And everything is then Euclidean, and then it's not so important anymore that there is sort of this normal direction where you've picked your time direction. That's a good question, yes.
But the linking is not well defined when it's not compact, right?
That's true. Yeah, I mean, it's still, in this case, then it becomes slightly trivial, right? Because the point is on that spatial slice. Yeah. So it's almost automatic, right? So in this sense, it's a little artificial. But when we now abstract from this and do this P-form symmetries and so on, it'll be clear then, in Euclidean signature, then these are compact spaces. We can fill them, and they actually will then precisely characterize these type of linkings independently of, how you've picked a particular time direction, because we're really in Euclidean space. Any other questions? Okay, so far we actually haven't really defined the topological operator, and I'll now do that, and then it'll be quite clear why, in this case, also the standard global symmetry is generated by a topological operator. So let's say we have. So now let's consider U1 global symmetry. For simplicity, this also works for, of course, other global symmetries, but to be specific, then I'll define sort of a topological operator. So G is in U1, and I'll write G as e to the I alpha. So this is really something, a topological operator of dimension d minus 1 labeled by this group element. And I'll define this to be the thing that does this type of an operation. So e to the I alpha on some d minus 1 manifold as just e to the I alpha q of. Okay, and so now if I insert this into these type of correlation functions, so then an operator OP will be charged with the charge e to the I alpha. So here I'm assuming the operator has some charge q, say e to the I alpha q times the linking of p and d minus 1. And again, the reason why this is not topological is, again, this charge really is independent of the specifics of this manifold, except for this topological invariant, which is this linking. Yep.
Is charge function of the operator at some fixed point of the theory?
So this is actually, you can do this at the UV, you can do it at the IR. This actually is just a statement about if you have a global symmetry, and in this case, these type of symmetries that act on local operators, you can always construct such a d minus 1 dimensional topological operator, and it will take this kind of form. And I can, of course, now also see why these are operators. So these d minus 1 g of m d minus 1. I can now insert the two of these. So with h. And of course, I can now, in this case, this is quite trivially, just g times h. Okay, and in this case, when h is g inverse, you would then call this object here dg times h is just going to be sort of the identity operator. And so in this way, you can compose them, and they would precisely mimic the composition that you know from the U1 group. Okay, so this I also don't use. So once we have, yep. Please shout, yes.
Given this idea of dependence of L and phi, like on the shape of MD minus 1 is L, these operators also, the only dependence they have on this MD minus 1 is whether it contains the point P or not.
So the operator actually will be defined. So, okay, very good question. So I'm defining an operator on that some manifold MD minus 1, right? And so actually, at this point, I want to be slightly agnostic as to the operator that it acts on, right? So here we constructed it basically. We have a symmetry, we act with the symmetry on some local operator. Here I'd like to just define it on a given manifold. This is the object. And now I can act with it on a local operator. So this is like the difference between you define a group and you abstractly have rules, they compose, there's an inverse, there's an identity, and you represent it. So at this point, I'm just saying, given a d minus 1 manifold, I can associate to it this object here. And I would like it to be topological in the sense that when I actually, deform this slightly, I don't change the topology of this, it still stays the same. Okay, but this, yeah. Okay, so these d minus 1g are topological operators which compose according to the group composition so but G is in some group G, so here was a U1, but G can now be whatever group you would like. It can be continuous, can also be a discrete group. So this is where we'll abstract it in a moment. And they will act on local operators in the way that we described. So what I'd like to actually do is define sort of what a zero form symmetry. Of a QFT or D zero form symmetry are the D minus 1 dimensional topological operators. And we should, I think here, very rightfully also say that, of course, we would like to have them act as, faithfully and linearly, in this case, if they're groups. But here I'm just saying these D minus 1 dimensional topological operators are generating the zero form symmetry. And for today, we assume that these form groups. And that's just what you know as a zero-form symmetry or global symmetry. Okay. And once you have this definition, you can, and okay, maybe I add one more word here. And so in the act on zero-dimensional operators. So once you have this definition, it's quite natural to just replace this with P. And here we have to replace this with D minus P plus 1. So codimension P plus 1. And they will act on P-dimensional operators. So a P-form symmetry is now just extending this to different dimensional topological defects. So operators like this, they are topological. They're now defined on a codimension P plus 1 manifold inside your spacetime. And they will actually act on P-dimensional operators. And we'll see this in a moment. So this part is sort of something we need to check how exactly this linking extends. But I can define, first of all, what a P-form symmetry is, just in terms of this definition. Yep.
So can you expand that sentence again? What does that mean by this zero-form R, the logical operator?
So if you have a quantum field theory, and you ask yourself, what are the codimension 1 topological operators? Now, in the examples that we looked at so far, they're all like groups. They're like your global symmetry. So if you have, for example, a global symmetry, like constructing, right, you have some Noether construction and so on, then they'll be just part of the zero-form symmetry. But I'm letting myself be a little bit more general here, because I'm not saying that they are the zero-form symmetry group generators. I'm saying they could be just all topological defects of this dimension I declare as the zero-form symmetry of that theory.
So by the T minus 1 dimensional logical operator, it means a set contains all possible G and all possible M T minus 1.
Yes, so but I'm not actually specifying necessarily that there is a G. So here, I'm being a little bit, okay, so we can do this in 2 steps. The first statement could be the zero-form symmetry group of your QFT is the set of all topological defects which also compose like groups. But I'm not actually saying that that's necessarily what I will call the zero-form symmetry. It can be more general. And this is sort of hinting at this thing at the very end of my introduction. You could have compositions that go beyond that, right? But indeed, that's why I'm saying for today, we'll look at just groups. So they're actually precisely of this form, yeah?
How strict is this notion that a P-form symmetry acts on a P-dimensional object?
Yes, so we will discuss this. Exactly.
The more fundamental thing is like the dimension of the topological operator, right?
It's the relation. Again, here it was important, you have a point, and you have a D minus 1 dimensional topological operator. And in the end, let's do this in here it's sort of a 2-sphere, and a point inside. So I can fill the sphere and become a ball, and then the ball, it's basically the P is inside this ball. And in this sense, they link.
If I have like a TFT with a zero-form symmetry, there's no local degree of freedom. So like
Okay, absolutely, yes. So, but still, you will have some kind of notion of, a topological defect or something.
okay.
So I think maybe you're talking about a symmetry-protected phase. That's a slightly different thing, but
I guess I'm thinking of like condensation defects or something. But I'm just wondering if you're including the P-dimensional operator as like a definition that there has to be a P-dimensional operator for it to be a P-form.
Okay, so they will act on, comes after groups. It's this might say, so this is the definition. And then I'm saying, today we're focused on groups, and these things will act on extended operators, right? This is not true when, maybe we'll get there at the end of maybe the 4th lecture or something. When you have more general symmetries, this is not the story. There's actually much more, even in fact in zero form symmetries, but yeah. Yeah, so condensation defect indeed would not necessarily in local operators, yes. Mm-hmm. So that can also happen, but that's sort of an additional thing. So indeed, you can have such phases, and that's sort of something which, again, goes under the topic maybe in lecture 4 when we look at more general kind of representations of these things. So indeed, you can accommodate that as well in symmetry fractionalization. Yep. You guys are running before we can walk. So you're like on a marathon already. So the short story is, even for a zero form symmetry, there can be higher representations. Now, that's all I will say about this. You can ask me afterwards. We wrote a 100-page paper about it recently, and it's a very exciting story, but I need to first get through the fundamentals. So getting off the chair, making my first steps, okay? All right, any other questions? Well, this is actually really exciting because even for zero form symmetries, there's something new you can say about its representations on extended operators. And I'm not discussing this in lecture 1 yet.
I know what the symmetry is. How can I interpret this as a topological, symmetry?
Okay, so here the way I derived it is using a current, right? Yeah. So what this definition actually allows us to do is to just say we don't necessarily need a current here. This is really something right here. Even when I then restrict to groups, I didn't say finite, a continuous group like U1 or whatever. I can just say there is some group G. It could also be a Z2. And I would just define this operator acts in the following way. So we will write down explicit expressions for these operators, but for this we need to actually first write down how to even talk about background fields and these kind of things. So we'll get there. Okay. Okay, so where were we? Right. So the definition that I like to use a P-form symmetry group is then something which I'll denote by G with some superscript P, is generated as generators that are B minus P minus 1. So they're codimension P plus 1, topological operators. And they will compose, I won't do the subscript now, but they just compose according to K, where G times H is equal to K in G. So how you see, and this is actually an exercise that I want you to do. We did this here. It's actually conveniently on this board that you can't see. And here we did this linking story with a local operator by having a current that's a one-form current. So now I will claim, so you can check, so like in this Noether story, analysis of what we would now call a zero-form symmetry, you can see that for a p-form symmetry, continuous symmetry, you will have a p plus 1 form current, now jp plus 1, and you can play the same game, and you will find that they will actually link. So this delta function on the left-hand side here will be with p-dimensional extended operators OP. So let's call them, OP, but then the subscript is P, and they'll sit on some manifold MP. So before it was O0 at a point P, and now we're just replacing this with a manifold MP. So for example, the case maybe you're most interested in is 4 dimensions, 4 space-time dimensions, and you're considering a line operator. So when d is equal to 4 and p is equal to 1, looking at line operators, and we can actually construct the topological defects that generate this one-form symmetry as topological surface operators, and these are called topological. So let's see this actually in an example. And the classic example of 4-dimensional theory is U1 just Maxwell. So U1 gauge theory in 4 dimensions. We have a gauge field and a field strength, and our equations of motion and Bianchi's tell us star F is 0. And so now here the star is precisely as I defined it there. So there's another 2 form. And I can now construct the following topological defects. D2 alpha of M2 to take a 2-dimensional manifold closed, alpha is a parameter, and star F. I can just construct this for U1 gauge theory, this operator, and there's sort of an analogous one, D2, if you call this here maybe electric, and this here magnetic. So once I take star F, and here I take F, these are topological because if I make small changes to M2, thanks to these equations, right, they're immaterial. And now the question is, how do I see that I actually talk to, well, what are sort of the charged objects? The claim is these are line operators, and indeed we'll see this in a moment. In this particular example, these are just Wilson line operators. the charged one-dimensional operators or line operators, which are just labeled by some charge Q. So maybe I should call these here now O1, but since they're Wilson lines, let me just call them W. So these are on some manifold M1, and they're literally just, because there's just U1, they're just e to the I Q integral of A over M1. And I can also define sort of, let me focus on the electric version. For the moment, there's also sort of an analog magnetic line operator with the dual field AD. Okay, so how do I actually think about these operators? These are line operators. So in a projection to a three-dimensional space, what essentially happens is that the topological defect so this is our D2 alpha E on some two-dimensional manifold I'm showing in a one-dimensional projection, and they can now link with this W of charge Q along this subspace M1. And now the point is, in 4 dimensions, a surface can link with a line. If you think in terms of a 3-dimensional picture, which is actually the picture I'm drawing here, a line can link with another line, right? So the D dimension, so in D goes to 4 dimensions, a surface, so a 2-dimensional operator links with a line, a 1-dimensional operator, and basically the charge is now measured exactly by this link. So you can actually fill in this with a 3-dimensional ball and then compute the intersection. Oh, really? Okay. So, wow, I'm going, yeah, you're on a marathon and I'm actually very slow moving. So let me just write down this, and then actually I would like you to ponder how you would show this. So when I act with this topological defect on this line operator, it precisely gives the charge. So alpha was this U1 generator, labeling the generator of this U1 one-form symmetry. Q is the charge, and this acts with this. And crucially here is again the linking. Of M1 and M2. Okay, so again, it depends on the linking, and that's always the thing that will extend to any dimension, any p-form symmetry, and p-dimensional operators. Okay, are there any more questions? Yes?
So if I take 2 such topological operators, can I not move one past the other?
Ah, indeed. Good observation. So if, fantastic observation. Now, if you are a codimension 1 operator, so 0 form, you can't, right? There's not enough space. But any other one, you can. So in fact, a p-form symmetry, so a GP for p bigger than 0 will always be abelian for exactly the reason that you're saying, right? So it doesn't matter whether I do this or that. I fuse them like this or I fuse them like that, because I can move them. There's enough dimension to move them past each other. And that's why, indeed, GPs are abelian. But G0 does not need to be abelian, like, as you know, right? Any other questions? Yep. Yeah. That's right, they are on the same M. So the way you should think about this is, let me draw one more picture and then I'll finish. This composition you should think of as follows. Essentially, I'm placing, so this is some d minus p minus 1 with g, and I'm composing it by sort of stacking them on top of each other and putting them together and saying that should be the same as putting just, so this is the one with h, and this is g times h. Right? And now the case that's sort of not group-like, you would get additional terms here, like sums of defects. But they're all defined on that one md minus 1.
Yeah, but is there a composition rule for that different?
Well,
I'm asking because like I'm trying to track in what sense this P-form symmetry group is a group.
So one way you can, so I'm actually trying to, sort of on a given manifold, right, trying to compose them. So for example, if you take two of these with alpha and with beta, right, you have only a well-defined composition if M2 is fixed, right? So in that sense, you're defining it associated to a given manifold. There's a more complicated structure, but for group-like things, I think you really, this is all there is to it. Yep. Indeed, yes. So Q, so this is why I did not get to, but Q indeed should be in Z. And in fact, that's absolutely crucial. So alpha, right, was parameterizing an group element in U1. Right, so this alpha, where did it go, was giving us a U1, this is a one-form U1 symmetry. And in fact, the statement that the charges are in Z is a statement that sort of the Pontryagin dual group, so the characters of this U1 are actually precisely Z. So indeed, there's this, again, we ran out of time, so that's why we didn't say this, but yeah, absolutely.
Well, why don't we stop here? Let's thank
Okay.
Sakura.
Yeah, please. Yeah, you just come and ask me, please.